All right, so we have a train, a choo-choo, pulling 3 cars. They have mass. The cars are connected by little metal bars, and the engine accelerates at a rate of 2. Assume the cars travel with no friction. Ha ha ha. So what we want to do is draw free body diagrams showing and labeling the forces exerted on each car. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. Distinct arrow, blibbity blibbity blah. All right, so if we have 3,000 kilograms, so 3,000 kilograms is going to have a force of gravity. It's got a big force of gravity. And then this one's 2,000 kilograms, so it's going to have a little bit less force of gravity, right? Because 2,000 kilograms weighs less than 3,000 kilograms. And this one's 1,000 kilograms, and it's going to have the smallest force of gravity. Because 1,000 kilograms weighs less than 2,000 and 3,000. All right, they're each going to have a normal force pushing up on them from the ground, which should be the same as the balancing the force of gravity, because there's no rope pulling at an angle or anything, so we need to make sure these are the same. I'm just eyeballing this. So this is normal force, normal force, normal force. Okay, so they all have a normal force, and that's it for the vertical. So now we have a choo-choo train. So we have a tension here. So on number 1, we have a tension on each side, right? So we have the choo-choo train pulling, and it's supposed to. So I'm not really sure how hard this is pulling compared to these, but I'm going to say this has got a lot of load here. So I'm just going to draw like F2 like this. Seems like this tension would be more than this, like this 3,000. I don't know how much the engine mass is. It didn't tell me. Okay, so number 2 has got 2 tensions on it. It's got F2. It has to be that this F2 over here has to be the same length as that F2, because they're the same thing. They're just pulling in different directions. This one's being pulled that way, and this one's being pulled that way. All right, and then this has got this F3 thing going on here. So it's being pulled by 3,000. So that's F3. This one's just got an F3 here. All right. So our expression is MA equals the sum of all the forces. So the mass of the first one is 1,000 times 2. A is 2, given, equals F1 minus F2. Here we have 2,000 times 2, which is equal to F2 minus F3. Here we have 3,000 times 2, which is just equal to F3. So F3 is equal to 6,000, right? So we could actually figure out what maybe we are supposed to do that later. F4 is equal to 4,000 is the difference between those two. Well, we know this one's 6,000, so F2 is 10,000. Oh, F2 is huge. And then this one's 2,000 equals that equal to F1 plus 10,000. So F1 is actually 12,000. So we can actually figure out what they are. Right, I mean, you have the information here to actually figure out what their values are. So F1 is actually the great. Well, that makes sense. The bigger tension here is it's pulling all of that crap. And then another next bigger tension here because it's pulling that. And then the least tension here because it's not pulling anything. It's being pulled. All right, that's 4 minutes. The dots below represent 3 different systems. Draw free body diagrams showing and labeling. The dots below represent 3 different systems. Draw free body diagrams showing and labeling the forces, not components, exerted on each system. Draw the relative lengths of all the vectors to reflect the relative magnitudes of the forces. What? Forces exerted on each system. Forces on the system of the 2,000 kilogram and 3,000 kilogram cars. Okay. So this is like both cars together? I guess there's a force of gravity and the normal force. together, and to both of them together, they have an F2 pulling this way, if they're one thing. Okay, so now here we have the 2 and 1 together would be 3,000. Oh, this should be force of gravity. Normal force. This is force of gravity. Normal force. And now the 2 and 1 together have the 2 and 1 together, they have an F1, and an F2. Should be the same. These should be the same. The forces on the system of the 3, 2, and 1, so they have a huge force of gravity, huge normal force, and altogether they just have F1, a big old F1 pulling on them. All right, so what do we have here? We have 5,000 times 2 equals F2, 10,000 newtons. Hey, that's what I got before. Here we have 3,000 times 2 equals F1 minus F2. And here we have 3, 4, 5, 6, 6,000 times 2 equals F1, which is 12,000. Hey, I got it right. And if we know this, 12,000 minus what is equal to 3,000 is equal to 6,000. That would be 6,000? Okay. 12,000 minus 10,000 is 2,000. 6,000? Yeah. Use the equations you wrote above to find each of the 3 tensions, F1, F2, and F3. Oh. All right. F2 equals 10,000. Right? That's just F1 is equal to 12,000. I feel like I did something wrong over here. Okay, so here, this is 1 and 2. This should be F3 here. That's what I did wrong. All right, so 6,000 equals 1 minus 3. But 1 is 12,000, so 6,000 equals 12,000 minus 3. So F3 is equal to 6,000. I can't read this. Without referencing any math or numbers, explain why F1 is the greatest tension and F3 is the smallest tension, even though F3 is connected to the greatest mass. So I think I did that already. I talked about that already, how F1 is the greatest because it's got the most stuff that it has to pull, right? And F3 is not pulling anything. It's just being pulled. All right, where are we at? 8 minutes? All right, we're at 8 minutes. Let's stop. And that was D. Oh, I need to stop.